Think about how a computer understands the word apple. It does not see a fruit. It does not taste sweetness. It sees a string of characters. To make sense of that, we convert words into numbers. This process is called an embedding. An embedding turns language into a coordinate system where similar concepts sit close together. If you put the word king near the word queen, the distance between them is small. If you put king near banana, the distance is large. This allows machines to reason about meaning without reading dictionaries. For years, the standard tool for this task was a model called BERT. It was an encoder-only architecture designed specifically to understand text. It worked well for a long time. But recently, a significant shift has occurred. Researchers have found that large language models are also effective embedding models. In fact, they often surpass traditional encoder-only architectures. This means we can use the same model to generate text and to understand text simultaneously. This convergence is changing how we build production systems. Here is the thing. When you use a large language model for embeddings, you are leveraging its internal representations. These representations capture semantic meaning effectively without requiring separate training. You do not need to fine-tune a separate embedding model for every task. You can leverage pre-trained large language models as zero-shot embedding models for tasks like semantic search and clustering. This bypasses the need for specialized embedding architectures. Now consider how this applies to engineering. One practical pattern is semantic caching. When your application receives a query, you compute its embedding first. You check if a similar embedding already exists in your cache. If it does, you return the previous result. This reduces the number of expensive application programming interface calls. It is like checking a library catalog before ordering a book. If the book is already on the shelf, you save time and money. This is crucial for managing costs in production environments. Another pattern is anomaly detection. Because embeddings live in a vector space, outliers become visible. Normal data clusters together. Strange data sits far away from the center. You can monitor the distance of incoming queries from the main cluster. If a query is too far, it might be an attack or a quality issue. This works for fraud detection or spotting drift in user behavior. You do not need to label every bad example to find them. The geometry of the space tells you where the anomalies are. Personalized recommendations also benefit from this approach. Instead of matching keywords, you match intent. You embed user history and item descriptions into the same space. When you search for items close to the user vector, you find things that fit their preferences even if they do not share exact words. This creates a more intuitive experience. The system understands the relationship between concepts, not just the text itself. However, there are risks. A critical consensus emerges regarding the interpretability of these embeddings. Contrary to optimistic assumptions, probing or feature mapping often reveals artifacts driven by dataset structures rather than true linguistic abstraction. Widely used interpretability techniques lack the rigor to validate internal model knowledge. This poses risks for debugging and deployment. You must verify that embeddings capture authentic semantic meaning without relying on flawed interpretability heuristics. Efficiency is another concern. While large language models offer superior embedding capabilities, balancing high performance with efficiency in low-resource settings remains a challenge. Handling long or multilingual texts requires specific pooling methods. You must consider how you extract the final vector from the model layers. Some methods preserve more context than others. Data bias is also a factor. The embedding space may reflect biases present in the training data. You need to ensure robustness against these biases before deploying to production. Mapping these embeddings through dimensionality reduction reveals that large language models organize concepts into intuitive geometric clusters based on semantic similarity. A surprising finding is that the embedding space of a large language model often correlates strongly with human intuition regarding concept relationships, even without explicit supervision on those specific relationships. But remember, the field currently lacks a unified, intuitive guide that effectively bridges the gap between complex vector representations and human-understandable semantics. Ultimately, the distinction between embedding models and large language models will blur. All large language models serve dual roles in both generation and representation. As an engineer or tech lead, you should rethink your architecture. Stop treating embeddings as a separate problem. Integrate them directly into your workflow. Use semantic caching to save costs. Use vector distances to find anomalies. Use clustering to understand user intent. But always remain skeptical of the math. Verify the meaning. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.